Yeah, so I'm gonna go through single phase motors, so our last mod in machines, and again, not probably one of the shortest ones. Again, single phase motors do have their place, mainly based on supply. Three phase motors are definitely more efficient. They perform way better, but single phase motors, again, if you have a 120 volts slash 240 volt service, so an Edison 3 wire like in your home, you're not going to have a three-phase motor because it would be costly to reproduce that supply potentially. So we have single-phase motors in our homes, in our furnaces, bathroom fan, air conditioners even have them. So you can get rated equipment for 120 or 240, and we'll talk about that coming up here too. You can have dual voltage motors, so like table saws and stuff for your garage, you still have a single phase service, but you can have a 240 volt saw as opposed to a 120 volt saw and draw less current. Okay, so there are those as well too. But again, they're limited, they're fractional horsepower sizes, so smaller horsepower, and their efficiency is about 60%. Okay, which again, compared to a three-phase motor, not very good. Most common ones that have two sets of stator windings, the current in one winding is caused to be out of phase with the other. This produces a rotating magnetic field required to start the motor. So if we don't have that second stator winding, we don't get that displacement between the two currents. So it'll just sit there and kind of pulsate, and the rotor won't start to spin. It'll just sit there and kind of vibrate. If you could spin it by hand, it would get it to start going. Okay, but the fact that we don't want to do that, and we want it to start on its own, we have to have two sets of stator windings to create that difference in the phase, to create a phase displacement, to get a rotating magnetic field that's similar to what we see in a three-phase motor with the separate windings 120 degrees apart from each other. Split phase motors are classified by the way the two windings are used to start and run the motor. So they got four classifications: resistance split, capacitor start, permanent split, and two value. So we're going to talk about the resistance split and mention the two capacitor value as well. Resistance split induction motor, again, the single phase motor with two stator windings uses windings with different values of resistance and inductance to create a phase angle between the two currents. So again, if we have a more inductive set of windings and a more resistive set of windings, those currents are going to be farther apart from each other, so we can actually create some displacement and get two magnetic fields in the stator that will allow our rotor to start to spin. So the basic components of the stator are the frame, the rotor, its centrifugal switch. The stator consists of laminated steel core slots to hold the insulated windings. The main or run winding has large copper conductors mounted on the bottom. So here's our main winding down here. And then our auxiliary or start winding are made of smaller conductors with fewer turns. They have a greater resistance and less reactance, so they'd be more in phase with the supply. And they're mounted on top of this stator slots. So you can see them, they're smaller and they don't take as much room. And they are only in there for starting as well too. So that centrifugal switch that they're talking about is what cuts this out after it gets to a certain speed. So the start winding of a two-pole motor has the center of the start winding placed 90 degrees from the main. Four-pole has the windings 45. Okay, so we can see this four-pole where we get, again, this is, the blue is all one winding and the brown or copper would be all one winding. The frame again holds, closes the stator. It's got the support for the shaft for the rotor, for the bearings, so it can turn freely within the stator. The rotor itself is very similar to a three-phase induction motor, so we have rotor bars here that are closed with end rings. So we do, when we get a voltage induced in here, we do get current flowing through here because they are complete path. They will have a fan on potentially as well too to cool. And here's that centrifugal switch. Now again, it's the force of the spinning that opens this switch once we get up to speed. So it has to be physically mounted right on the shaft. Okay, so because it's the spinning that actually the force of the how fast it's spinning is what opens the contacts and takes the start winding out of the circuit. So centrifugal switch again serves as a disconnect for the start winding when it nears full load speed. Okay, and it's going to open it around about the 75% of rated speed of the motor. So we don't want that start winding in during the running portion. We just want it for starting, and then we'll cut it out. So when it gets almost up to full speed, that switch will open, and then we just have our main winding during the run scenario. Other ways we can do start winding cutout are with the current sensitive relay. We take advantage of the high inrush current that will pull in a set of contacts that closes the contacts for the start winding, so that the start winding is now in the circuit. And then as the motor gets up to speed, it draws less current, and that would de-energize the coil for the relay and open the start winding circuit. The other way is to use triacs and solid state controls. Again, both of these scenarios can be located remotely. The centrifugal switch has to be mounted on the shaft. The current sensitive relay and electronic switching device like solid state device can be mounted remotely, okay, in a separate location. Principal operation of a single phase motor, the run winding produces a pulsating magnetic field and not a rotating magnetic field like in three-phase. So in order to produce the rotating magnetic field to develop torque, then we got to get that rotor spinning. The additional means involving a start winding is required. So the run winding is made of, again, larger insulated conductors with more turns mounted on the bottom of the stator. The start winding is connected in parallel with the run winding and is wound with fewer turns of smaller insulated conductors. It is mounted at the top of the stator slots and occupies fewer slots than the run winding. Okay, so just kind of repeating what they talked about previously when the design. And we'll show a phasor diagram here in the next slide too that'll help with this. And during starting, again, the start winding with higher resistance, lower inductive reactance, has a current that is more in phase with the applied voltage. So again, closer to the zero reference. And the main winding has lower resistance, greater reactance, so it's going to have more of a lagging current than the start winding. The two fields produced by the winding are out of phase with each other and build to a maximum at different times. This creates the rotating magnetic field that's similar to one in a three-phase motor. So again, if we can get this phase displacement here between the start and the run windings, it shifts our sine waves so that they're peaking at different times. And what that does is basically creates rotating magnetic field, because as the poles, we have a pole, sitting at one point, and then another pole over here will become energized later, and it causes the rotor to kind of chase those magnetic fields and start spinning around. So the rotating magnetic fields induces a voltage and current into the rotor, again, because it's a closed circuit by having those end rings on the rotor bars. So whenever we have, again, now we have something spinning within a magnetic field, we get voltage induced, we get current because it's a complete circuit. And then the interaction of the rotor flux and stator flux produces a rotational force or torque, and the rotor and the motor starts to turn. So starting torque would be greatest if the displacement was 90 degrees. However, in this resistance split motor, it's around 25 to 30. So their starting torque is poor. The starting winding is only in the circuit until it reaches about that 75% rated speed. At that time, the rotor develops enough magnetic field intensity to produce the cross field theory. If the winding was left in, it would burn out. Okay, so we definitely have to have that start winding cut out, because it's not rated to be in there during the run, and it would be at the expense of it. So again, here we have our supply coming in, that green, so that's in phase, okay? And then we see these currents are different based on the design of their windings. So our start winding, get a little bit more resistive, less reactance, so it's closer to being in phase. And then our main winding, more reactive, less resistive, so lagging more and creating a displacement between the two currents. Okay, that basically creates a scenario where we can have a rotating magnetic field within the stator, which will help the rotor start to turn. Okay, that cross-field theory again is used to explain motor operation once it's running. So when we're running again, now the start winding has been cut out. When it's the rotor's turning, the currents flowing in the rotor circuit lag the induced rotor voltage by 80 degrees. Okay, so not the supply, the rotor voltage. This is because it has very little resistance compared to the inductive reactance within the rotor itself. The magnetic field produced by the rotor is almost 90 degrees lagging the stator field. This cross field interacts with the existing stator field and produces rotational force or torque. The cross field effect is as if there's another stator winding that's been placed at right angles with the run winding. So it simulates a two-phase system with a displacement of 90 degrees rather than the three-phase at 120. So basically once it gets started, the two magnetic fields are interacting with each other and they have a displacement, so it kind of helps the rotor keep spinning. Okay, so that's what that cross field theory is the magnetic field on the rotor is interacting with the magnetic field of the stator and basically is enough to force, and there's enough displacement that allows the rotor to just keep spinning once it's up to that speed. Motor characteristics, again, I kind of summarized what's in your ILM. The resistive start induction motor is considered constant speed with good speed regulation from around 4 to 6%. The slip is usually around 5%. Okay, most are 4-pole with their, again, a rated speed of 1725. Two-speed motors with two sets of windings are used for some applications. Most common is quarter horse. Can be rated for single or dual, and we'll talk about that coming up here. Starting current is about 5 to 6 times, so that's where we're taking advantage of that high starting current using a current-sensitive relay for the cutout, if we would choose that instead of the centrifugal switch. Starting torque is around 125 to 150% of rated running torque. So again, not very good starting torque. High noise factor caused by the pulsating power of a single-phase motor. Can either be started in either direction. Direction can be changed by interchanging the leads to the start winding or the run. Okay, not both. If you change to both, you would not really change the direction at all. So they are reversible, not reversing. So reversible means that it can go the other direction. When it is stopped, we can change the wiring. Usually use the start winding, the T5 and T8. We switch those leads. They cannot be reversed while running because the centrifugal switch or the start winding is not in the circuit anymore. So it can't just stop, go back in the other direction without the start winding being energized. So it can go the other way, but we have to stop it first and then switch the leads to do that. Because they are relatively inexpensive, they are very common. Again, used in furnaces, washing machines, drill presses, fans, sump pumps. Okay, then they talk about the two-value capacitor motor, but I'm just gonna kind of go back to this, a little bit of a drawing here that I have. I'm just gonna go to my camera. So I kind of just have this drawing here. It's very similar to what's in the module. Just kind of wanted to show some of the magnetic field to get this thing to start to spin. Okay, so here's a reproduction of the phasor diagram in the module. So here's our phase voltage, our current from our run winding, and our current from our start winding. Okay, so this is our start, just like what they had in the module, and then our displacement is 25%. So what that does is show that there's a difference between the peak from our start winding to our run winding. Okay, and I drew these 45 degrees apart, but again, usually that 25 to 30 degree displacement. So what happens is, if we're looking at this at 90 degrees, okay, so at 90, my start winding is peaking. So let's just say we start with this pole here. It's at a north, a south over here, and again, if this is a 4-pole machine, same winding, just more poles. Then I have another north here and a south over here. What this rotor is going to do, that basically has its own magnetic field is going to try and hook up to that north pole. Then the main one, as the start winding goes, it's going to start to drop. As it's dropping, rather than the rotor kind of not knowing where to go, we have this second winding, the run winding, that's going to peak right after. So then this becomes the north. So with this south pole, it's going to start chasing those norths around. And again, this is a snapshot in time here at 90 degrees. As we go down to 270, then these poles change. So this becomes north, this becomes north, this becomes north, this becomes north as we're rotating around because we have alternating current. So the poles will change as we go from a positive alternation to a negative, which basically allows the rotor to start to chase the magnetic poles around, and that's what starts it spinning. If we only had one winding, again with one set of poles here, even though these would change from north to south as we alternated, the rotor wouldn't know which way to go. It would just sit there and basically vibrate and hum, okay, because it has no other pole to try and catch to start spinning around. So what it does is it just sits there and vibrates. We put these other windings in to create a second current, so a second magnetic field, so that that rotor has something to start to chase around. Okay, so hopefully that helps. It's very similar to that video that's also posted, so have a look at that as well too for some help if this module is still kind of giving you the gears. So I'm gonna keep going about this 2-value capacitor motor. The best performance from a split phase is provided by a 2-value capacitor motor. Combines the advantages of capacitor start and permanent split. The components, again, centrifugal switch, the start capacitors in series with the start switch. This is the short time electrolytic, this guy right here, and a run capacitor in series with the auxiliary winding. Okay, so they're in parallel with each other, but in series with the auxiliary winding. So here's our oil field, continuous rated. Again, short time, this is in series with this centrifugal switch. The centrifugal switch is going to cut that out once we get up to speed. Okay, so capacitor start, capacitor run. So this capacitor is still going to be in the circuit when it's in its run condition. Applications of the 2-value capacitor, they're expensive, okay, but their excellent start and run characteristics offset the cost. It's quiet, has a good power factor, typically low noise, high starting torque. Okay, so a significant advantage over the resistance split. We use them for AC, compressors, refrigeration units, etc. So now we're going to talk about dual voltage. Again, you could have a scenario where you have the availability of 120 or 240 volts. Again, we draw less current on that higher voltage, so it could be an advantage. Some motors come with 9 leads if they have thermal protection. If they don't, they'll have 6. So in this scenario, we see there's 2 main windings and 1 start winding, so that's where you're going to get your 6 leads from. Again, the thermal protection adds more, and we'll see that coming up here. Okay, so 2 leads brought out from the start, and then 2 leads from each winding, so that's the total of 6. Okay, again, this is a drawing of a general single-phase motor. The numbering could be different depending on the motor you buy. It could be colors. Okay, so check the nameplate, of course. This right now is wired for the low voltage connection. These windings are all rated for 120 volts, the start, the main, each main. When they're hooked in parallel, as they are right now, each winding would be ready for 120 volts. Okay, because when they're in parallel, we would maintain that voltage. So here's our centrifugal switch, again, cutting out that start winding once we get up to speed. And here's the 2 windings for the, or here's the 2 leads for the start winding that we could switch if we wanted to reverse the direction. Again, as long as it's at a stop. With T5 and T8, it's going to be the easiest thing for us to switch. Here's the drawing for the high voltage connection. So now these main windings are in series, again, still rated for 120 volts. This guy too. So we have our different connection here, line 1, line 2. Again, these windings are connected in series now, and important too to show that that start winding is still rated for 120, not 240, so it wouldn't go across the whole winding It's just going across one of these main windings, so that this, because this is only rated for 120 volts as well. Okay, if we put it across both, obviously this would see 240, and it's definitely not going to like that. So integral thermal protection. CEC requires that motors be protected from overheating due to overload. Protection may be separate, but it could be internal. Okay, so sometimes a lot of these motors have internal thermal protection, and if they do, they'll have more leads brought out too. Okay, here's the often used disc type manual reset. Protective device is a switch that's responsive to current and temperature. Some are temperature only. Again, I associate an increase in current with an increase in temperature myself, depending on the amount of current, of course, and for how long. But for an overload, we would be seeing an extra amount of current for a significant amount of time, which would create a lot of heat, which would trip this heater and open the circuit breaker component. And then it has a manual reset here. Okay, so these need to be in series with the line coming in, because we want to open it and disconnect the entire motor circuit, not just part of it. So if we have, again, these thermal protection, we could potentially have our line 1 and 2, the 6 leads from our windings, and then also the P1, 2, and 3 from the thermal protection. Again, these could be done internally, where all they do is bring out P1, but you could have to be the one that hooks T1 to P3, T5 to P2, and L1 to P1. Okay, so those would be, again, you check the nameplate and it would tell you. Again, dual voltage, so this is our parallel connection. So our low voltage connection, we'll show the series connection for the high voltage as well too. It's just a little bit different on the thermal. Okay, so here's a high voltage connection. Again, now they're in series. Still have our start winding, again, just parallel with one, rated for 120, 120, 120. But when we hook these in series, we got 240 here now. Different because we don't have the start winding coming in here. So we just have the P1 and P3 terminals to worry about. Again, the nameplate would show you exactly what you need to do for the low voltage or high voltage connection. Okay, so that's kind of the gist on the single phase. They only talk about the 2 types as opposed to all 3, but have a read through that, go through the blackboard. There is a review also posted in the course that you can do for practice for the test. So let me know if you have any questions.